If you unplug your TV from any cable or aerial, you get this snow, this white noise. What causes it? And how does it relate to the creation of the universe? Albert Einstein was born in Ulm in Germany in 1879. He wasn't a particularly brilliant student, but he wasn't a bad student. There are some stories saying, oh, he was late in talking or walking on, that sort of stuff, or he was no good at school. Everybody develops at a different rate, and you can't really tell what people are going to like and what people are going to produce later in life by how they perform earlier on. So there's nothing to say that he was remedial or anything like that. He was average in many respects. But he did have a few characteristics that did change the course of his life, and that was he was very antagonistic and cantankerous with his tutors. He was always asking questions and being facetious, and I think that's probably the reason that he didn't get a prestigious place at university later on. He did go to Zurich Polytechnic. Now, a polytechnic is a more vocational based university, one that focuses on practical applications of subjects rather than perhaps pure academic subjects. He got a degree from there, but he couldn't do any postgraduate work because no professor would take him on. Why would they? He was annoying and he criticised people. So he ended up getting a job in a patent office. Now, I'm sure you know what a patent is. It's a way of formally documenting an invention. But Einstein was a patent clerk, so his job was to file the patents. It's quite a mind-numbing, well, not mind-numbing, but quite a tedious sort of administrative sort of job. Not one that would tax the intellect, for example. But it was very useful to him because while he was there, he was able to think. He was able to think about physics, and he was able to think about the puzzle that had dominated his sort of waking life for many years. And that was about the nature of light. And he asked himself questions. What would happen if you were travelling at the speed of light and you held out a mirror in front of you? What would you see? Or if you were travelling on a train that was travelling at the speed of light and you turned the light on, what would happen? These questions and others allowed him to think thought experiments about how the universe could actually be working behind the scenes. And it's these thought experiments. Other people did practical experiments. Einstein didn't do that. He did theoretical experiments, thought experiments, and he worked out the mathematics. Other people proved him right subsequently. And in 1905 he published, as I said before, 5 groundbreaking scientific papers, even though he wasn't attached to a university. Now listen to the titles of these. The first one in 1905, his miracle year, was A New Determination of Molecular Dimensions. Now in that paper, Einstein told us for the first time, proved to us that atoms exist. Before that it was theoretical. His second paper, On a Heuristic Point of View Concerning the Production and Transformation of Light. That was in June 1905. That was the dawn of quantum physics. That particles and waves behave as the same. Waves are particles, particles are waves. Then, in July, On the Movement of Small Particles Suspended in Stationary Liquids. This was the third paper, and this proved that atoms existed with a theoretical experiment that had been carried out, and he put the theory behind it, and it proved the size of atoms and the existence of atoms. The fourth paper in September of 1905, On the Electrodynamics of Moving Bodies. And it's this paper that we'll be looking at in more detail. This is relativity. This is our topic. A few months later in November, he published a sort of, the fifth paper was an addendum to that, a sort of an appendix to it. And it was called, Does the Inertia of a Body Depend on its Energy Content? Otherwise known as E equals mc squared. And it was the famous equation was first quoted in that paper. So we're going to look at relativity. But beginning with, we're looking at light, the nature of light that had been described by Michael Faraday decades earlier, mathematically explained based on Faraday's work by James Clerk Maxwell, and that the electric and magnetic component of light was an electromagnetic wave which travelled at the speed of light. In 1929, we didn't know how big the universe was. We thought that the Milky Way was the universe, and this is why if you look at old books or old films of the time, you'll see that they'll talk about galaxies and universes being the same thing. That's what we thought. But there was a strange group of stars called Andromeda, and Edwin Hubble looked at it through a massive telescope and saw that it wasn't just a smudge, it was what looked like another Milky Way. And it became known as an island universe, a universe beyond our universe. Now, of course, we say it's just the nearest galaxy to the Milky Way. Edwin Hubble studied it and he measured the distance to it using a variety of clever methods. And he found out that it was much, much further away than we'd ever thought. It wasn't just right next to the Milky Way, it was an unimaginable distance away. But he also noticed something else. That as he looked at more different galaxies, he found that the light that was coming from them was reddish, more reddish than it should have been. We call this redshift. So what he thought was going to be yellow looked more orange. What he thought was going to be orange looked more red. What he thought could be blue looked more green. So all the light that was coming from distant stars, distant galaxies outside the Milky Way, they were tinged with this red. They looked more red than they should do. Now, to his mind, this only could mean one thing. It was to do with the Doppler effect. The light from the stars had been stretched. What does that mean? Strange things happen at the speed of light. If we were talking about classical physics, about Newtonian physics, we could add velocities together. So if I had a gun and I was to fire it and the bullet leaves the gun at 700 miles per hour, which is the speed bullets leave some guns, then the bullet would leave my stationary gun at 700 miles an hour. Now, if I was travelling in a car, say the fastest car in the world, which travels at 700 miles per hour, and I was coming this way at 700 miles per hour and fired my gun, the bullet left the gun, what speed would the bullet be going at? Well, this is where relativity begins, because we're talking about relative to what? So, relative to the gun, the bullet leaves it at 700 miles per hour. But the gun is already going at 700 miles per hour. So the bullet, compared to some stationary observer over there, the bullet appears to leave the gun at 1400 miles per hour, double the speed. And if it hit that guy, then he would get the full benefit of a bullet travelling at 1400 miles per hour, not 700 miles per hour. Now if I was going the other way, what happens? So this time, I'm going the same way, but I'm firing the bullet the other direction. So here I am at 700 miles per hour, but I'm going to fire the bullet out the back of the car. So as I go, I fire the bullet leaves at 700 miles per hour, but the bullet was already going at 700 miles per hour inside the gun. So what happens to it? And the answer is, weirdly, it falls to the ground.
Let's say you're driving along in a car at X miles an hour. You throw something out the back in the opposite direction at the same speed. Does it just fall straight down?
Build an air cannon, fire a soccer ball at 60 miles an hour. We'll do it again inside of a moving vehicle going 60 miles an hour. See if the energies cancel each other out and we get a vertical drop.
Love it. Let's do it.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops and it just falls.
Look at that.
Fantastic.
I mean, look, it doesn't move at all. It's going straight down.
Dude.
Woo! We did it! We did it!
But what would happen if it wasn't a gun, it was a torch? So imagine if I could go at the speed of light, and I've got a torch, and light leaves the torch at the speed of light, which is 3 times 10 to the 8 meters per second. So let's imagine I'm going at the speed of light. I can't, but let's go as close as I can. So I'm going to go in that direction at the speed of light. I've got my torch, so here I go. My torch is travelling at the speed of light, so am I, and the light is left the torch. Well, surely it's going to be going at twice the speed of light, because I'll be adding the velocities. And if I was doing the other thing that I did, so I'm coming this way, but I'm firing the torch that way, the light leaves the torch at the speed of light, surely the light would just fall to the floor. How can it possibly be? And the weird thing about this, which is Einstein's special relativity, is that the speed of light is constant and it doesn't change. Weird things happen at the speed of light. So to an observer over there, yes, I and the torch are travelling at the speed of light. The light leaves the torch at the speed of light. Weird, isn't it? So what actually happens? Thou shalt not exceed the speed of light. So nothing can travel faster than the speed of light, not even light. So the light leaves the torch at the speed of light in that direction, but as I move in that direction, the light wave gets squashed. And if a light wave gets squashed, then the frequency is going to change and the wavelength is going to change. Now if I was travelling this way again, but I'm shining the torch behind me that way, then the light is going to get stretched, the wave will get stretched. The speed of light can't change, only distance and time can change. So if a light wave gets stretched, its wavelength is going to increase, its frequency is going to decrease. So we're going to get a stretched wave. It's going to become more red if the thing is moving away. And if the thing is moving towards, then it's going to become more red. I don't mean it will be red, it will just become more squashed and therefore more blue. It will become in the direction of travel more blue. So if I was to get this torch and throw it towards you at the speed of light, this white light would look blue. And if I was to take this torch and pull it away from you at the speed of light, the light waves would stretch and it would look red. With sound, the Doppler effect is easy to understand. If you look at the fire engine on the left, and we've all noticed a fire engine, ambulance or a police car or something, or an ice cream van if it's going fast enough, if that's stationary next to us, we hear a constant sound. And that illustration on the diagram there, you can see the wave fronts demonstrated by the circles, that they're constant. The wavelength, the gap between the circles, is constant. But if you were stood in front of this fire engine, the wavelength, the waves would be squashed as they came towards you. And if a wavelength is shorter, that would mean the frequency would be higher. So you would hear a higher pitched sound as the fire engine came towards you. If you stood behind the fire engine and it moved away from you, then the wavelengths would be stretched, and the wavelength in those circles is definitely bigger than it would be if the fire engine was stationary. So you'd hear the sound of the siren stretched with a longer frequency, so it would be a lower sound. So as it came towards you, the sound would be going Nino, 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 and then as it went away, Nino, 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 like that, except it wouldn't be Nino, as you know. So this is what happens with sound. The sound of the siren will be higher when it's coming towards you and lower when it's going away from you. But if it's going past you sideways on, you hear no difference. You don't hear it. You only hear it in the direction if the sound is coming towards you or going away from you. It's squashed if it's coming towards you, stretched if it's going away from you. So what does this mean for Hubble and his redshifted galaxies? It means that if you had light and that light was coming towards you, then it would be higher frequency light, so it would look more blue. If the light was going away from you, it would be stretched, so it would look more red. So if galaxies are redshifted, what does this mean? It means they're moving away from us. The light is being stretched. But it also means that they're all moving away from us because they're all redshifted. If all the galaxies are moving away from us, what does this mean? it means that they must have been closer in the past. If they're moving away from us now, and they're moving away from us yesterday, they were closer to us yesterday, they were closer to us last year, they were closer to us 1,000,000 years ago, they were even closer 1,000,000,000 years ago. If we trace them back, all the way back, so they were all in the same place, and from that point they all expanded, that's the Big Bang. That is time equals 0. That is the moment of creation, as far as we know. It's very hard for human brains to understand something in 3 dimensions expanding into a 4th dimension. It's very difficult to explain. So if we reduce it down to something that we can understand, like a 2-dimensional surface of a balloon expanding into the 3rd dimension, maybe this will help. So here's a balloon, and I've stuck some stars on it, and those stars are to represent galaxies. Now look how close they are together. They're about 1 centimetre apart. So this is a very small universe. Now, as expansion happens and the universe expands, this is what happens. The space expands. The atoms don't expand. Space expands. So the universe is now 3 times as big as it was a moment ago, and look how far apart the galaxies are. They're about 5 centimetres apart. So this is inflation. This is the universe rapidly expanding from the Big Bang, which isn't really a bang, remember. It's a massive expansion we call inflation. And it's pushed the galaxies apart. And as this universe gets bigger and bigger, those galaxies will get further and further away from each other. But not only that, let me try a different version. Let's have a big crunch. This time, let me draw a wave onto my balloon, onto my universe. I've drawn a wave onto my universe. You can see it there a bit. It's got a wavelength of 1 centimetre. So let's see what happens when inflation happens. Sort of just about making out. Yeah, there it is, look. So there's my wave now. It's now got a wavelength of 5 centimetres. So the wavelength has increased as space increased. So this is what's happened to our light. As the light from the Big Bang filled the early universe, but the universe expanded, it stretched the light with it. So that light would have been gamma radiation to start with. But as it got stretched, it became X-rays. Then it became ultraviolet, then it became visible light, and the whole of the universe would have been glowing with light. Then it was stretched even more into infrared, and then into microwaves and radio waves, and that's where it is at the moment. So the universe is awash with microwave radiation, which we can detect with our detectors. And the simplest one that we've got to detect it is a detuned television. And that static is the afterglow of the Big Bang being stretched so that we can't see it with our eyes, but we can detect it. So if you've got a balloon, you could try it yourself. You could do a little squiggly wave on your balloon. You could do some little dots or stick some stickers on and try it yourself and see if you can see that's how the universe, that's an explanation of the Big Bang. It's a model for the Big Bang. It's obviously not correct because we can't imagine 4th dimensions. It doesn't make any sense to us. But it makes sense, the idea of those galaxies on a surface moving away from each other. But what about this? This was Hubble's next discovery. So this graph shows the blue dots are galaxies and how far away they are from us. And on the y-axis, we've got the speed that they're moving at. What do you notice? Well, hopefully you notice that the further the galaxies are away from us, the faster they are moving. Now, this doesn't make sense. If you think of an explosion like a firework explosion, the things are faster the closer to the explosion, and when they get further away, they slow down. Every firework we've ever seen, it bang, there's an explosion, the things move away, and they slow down as they get further away until they stop. But this isn't what's happening in the Big Bang. That's why the name Big Bang is a sort of, well, it was said as a joke initially, and it confuses us because we think of it as being an explosion. but it's clearly not, because the further things are away from us, the faster they are going. The explosion's speeding up. Doesn't make sense. So this was Hubble's conclusion, and it ended up being a law based on this idea. So to get a law named after you while you're still alive is quite something. This is how it works, and you can do a question based on it. So the speed of those galaxies in meters per second is the expansion constant, the Hubble constant, times by the distance the galaxy is away from us. So if we've got a galaxy that's 1.5 times 10 to the 20 kilometers away, how fast it's moving? Write your answers in the document. There are other similar questions there too. But this isn't our only evidence for the Big Bang. There are other things. So we come to this. This is pictured by the Hubble telescope, which is named after Hubble, many decades after his death, of course. This is scanning the sky, the whole of the sky around the Earth, and recording microwave radiation. Why is the universe full of microwave radiation? Well, hopefully we've established that it's there because it's the glow of the Big Bang, that gamma ray explosion that happened at the Big Bang, but that light has been stretched all the way into microwave radio waves. And the telescope can pick them up and give us a complete map of the whole sky. But you can see this for yourself. Turn on your TV and you'll see that static. That static is the microwave radiation, the background radiation, the cosmic microwave background radiation, the glow of the Big Bang.